So I'm really talking about kind of a work in progress here. We've been looking to use hyperoxia as a contrast agent, which we've done before in the past, but combine it with what's called a multiparametric qBOLD acquisition in order to try and measure oxygen extraction fraction and hopefully make this a more widely applicable technique. So start by saying, well, why do we want to measure oxygen extraction fraction? I think over the last few days, it's become quite clear why that's such an important measurement, particularly when looking at things like trust and looking at global measurements. The brain obviously constitutes a relatively small part of the mass of the body, but it does consume a lot more oxygen than its size would suggest. And as with most organs in the body, has very limited capacity to store oxygen in the case that blood supply is cut off momentarily or temporarily. So it's a key physiological parameter of brain's energy metabolism. And clearly there are some obvious applications. So in the application of stroke, and clearly in the PET literature, it's associated with looking for salvageable tissue in the penumbra, whether that might help you to direct people towards the right treatment, endovascular or medical. And then likewise in the study of gliomas, quite often people are monitored, their gliomas are monitored in order to see whether they might transform into a more aggressive type, which might require more aggressive treatment. So these are some of the more obvious ones, but obviously there's clearly a much broader range of things that might be applicable. So the way we choose to measure this, rather than using something quite global, which is shown to be very, very useful, we're trying to also see whether we can get regional information, which you can imagine would be more useful in a stroke. And so the way we approach that is by using a technique called quantitative BOLD. Now, often when I introduce this to people, they assume it's some sort of fMRI kind of measurement, so we must give some sort of stimulus. But actually in quantitative BOLD, we try and measure the resting BOLD signal. And so I'm not equally talking about resting state, I'm talking about just the contrast. So the contrast that's formed because of deoxygenated blood in the venous and maybe capillary vessels of the brain. And the way we can get at that information is by using a relaxometry experiment. So we're all really comfortable with measuring R2 and R2 star, but the difference between those two measurements is known as the R2 prime, which is the reversible transverse relaxation rate. And if we can also calculate the volume which is occupied by the deoxygenated blood, we can try and use that R2 prime measurement to extract estimates of OEF. So here's some example images. Whilst this paper by, you can't see the reference, but by here Yablonsky from 2007 was not the first quantitative BOLD paper, it's one which shows the principle very clearly and developed a much more elaborate model than the earlier works. So we have some sort of measurements of the R2 prime. In this case, we can see in this deoxygenated blood volume map that we've got contrast between the white matter and the grey matter, which you'd expect, a lower blood volume in the white matter. And then we get these relatively flat-looking OEF maps. Often what people strive for is this idea that the OEF is constant across the whole brain, although it's not entirely clear to me whether that's realistic in healthy physiology. It's just it becomes more from looking at PET literature where voxels are a lot larger and so the averaging is greater. In terms of practical side of measuring, trying to do a quantitative BOLD measurement, what I'm considering here is what the signal looks like. So if we can measure an R2 prime weighted signal, that will be the blue line here, and this is actually plotted logarithmically. So for a very long, so I should explain what this is. So the spin echo displacement time is basically the time delay between what would be a pure spin echo and introducing small amounts of R2 prime weighting. So for the very long tau values, spin echo displacement times, we expect mono-exponential decay. But for the very short ones that are close to the spin echo, it becomes quadratic. And so from the model by Yablonsky from many years before that, in 1994, we know that the R2 prime itself is proportional to the product of the volume and OEF. But if we can measure that R2 prime from these longer tau values, we can also extrapolate back to the intercept to calculate the difference between the intercept and the measured RT-prime-weighted signal at that time point. And that theory also predicts that that difference in signal is the DBV, is the deoxyribonucleic blood volume. So there's multiple ways in which we might choose to acquire data for doing quantitative BOLD. In that paper by Yablonsky and he and Yablonsky, they used a gradient echo sampling, a spin echo or Jesse technique. And this is very efficient, and you get very many closely spaced tau values for your RT-prime weighted data. And essentially what it is like an EPI sequence, but without the blips between lines, which allows you to get this very closely spaced echoes when you loop around to fill most of the K-space. But because you're changing the echo time at the same time as the tau value, you then have to fit for the R2 and the R2 prime at the same time. And so that makes things more complicated. But we can estimate, in theory, the DBV from the spin echo data within that Jesse data set. So that's nice and self-contained. What I've been using more recently is, and it's not a recent technique, this goes back a long way, the estimated spin echo, using the early days of fMRI, is an ASE. So the ASE differs in that you keep the echo time constant, we move the refocusing pulse around to alter our tau value. And by doing that, we keep the R2 contrast constant, and we just manipulate the R2 prime directly. So it makes the analysis much simpler. And again, we can estimate DBV in theory from the spin echo. But actually, in the last couple of years, Atlan's been doing a systematic review to sort of to better understand the landscape of quantitative BOLD in literature. And what's become very clear to us is that these two techniques, whilst they, to me, are intimately associated with quantitative BOLD, they don't really dominate in terms of papers that are published. So the most common technique to do these measurements is multiparametric qBOLD. And this differs in that you use a spin echo sequence to measure the R2 and use a gradient echo sequence to measure the R2 star, and then you're able to do a subtraction. But clearly now we don't have these values of the R2 prime weighted signal around the spin echo, and so we're not able to measure DBV in the traditional way. And so in these measurements, CBV is estimated using a gadolinium bolus tracking experiment, so by DSC, and that has other advantages because it's well known that the DBV and the LEF can be somewhat collinear in the analysis, and that can lead to multiple solutions that fit your data. In terms of these techniques that are most common, the Jesse and the ASE require a high SNR, but more fundamentally, it's limited in that these are all custom pulse sequences. So in the European context, then you lose your CE marking, and so clinical studies might become more difficult, and distributing different versions of software is always a pain. Whereas multiparametric qBOLD generally relies on product sequences, so therefore much more widely available. Obviously, a gradient echo is very similar across vendors, so they wouldn't have much problem translating it. But it does require the administration of a contrast agent, which probably happens anyway clinically. But more importantly, it measures total blood volume, not deoxygenated blood volume. So multiparametric qBOLD measures where we are typically considered to be either tissue oxygen fraction or a relative measure of OEF, because we don't have this very specific venous or deoxygenated blood volume. And here are some ideas of the values from the literature. So R2 prime is probably the order of 3 Hertz, 4.5 Hertz with Jesse, a little bit higher for mqBOLD, about 6 to 7 Hertz. OEF values do vary a little bit again. ASE is well known to have a slightly lower OEF than Jesse, and then again the mqBOLD is a little bit higher again. So one way we've tackled trying to measure blood volume, deoxygenated blood volume or venous blood volume previously, is to use hyperoxia as a contrast agent. So we can't really add a lot of oxygen to the blood because arterial blood's typically very close to 100% saturated in a healthy individual. We can put a little bit more oxygen into the plasma, and that spares some of the hemoglobin going into the venous blood vessels, and so we get it's quite a small signal, but we can actually get a signal that's dominated by venous blood. And by doing that, we can actually change the amount of or concentration of deoxyhemoglobin quite consistently across the whole brain. And when we measure that signal using a standard BOLD EPI sequence, we can then measure the BOLD signal change in response to our hyperoxia stimulus. And using the heuristic model, we can convert that into a measure of venous CBV. Here's some example images from a little while back, showing that you can clearly see this grey white matter. Oh, actually, maybe you can't on the screen. No, you can. Between the grey matter and the white matter, and maybe some larger vessels on the surface that show up. So the aims of the study are to try and improve the feasibility of qBOLD in a clinical setting. So clearly, being able to have a product pool sequence, which is already on the scanner, is very beneficial. But we want to improve the quantification of DPV, and we're going to use this hyperoxia BOLD approach to do that. And then we want to compare those measurements with whole brain OEF. So ideally, like go back to the old days of PET, and people used to do maybe like a Katie Smith type measurement where they might take blood samples directly. Clearly, that's not ideal in the modern era. So Trust gives us something very similar, but without all the messiness of having to do a cannulation in the jugular bulb. So, so far we've analysed 4 of our healthy participants in this age range of 18 to 40. We used a sort of relatively simple home-built gas delivery system, collaborating with a former colleague in Oxford, who's been building this very simple design, which we tried to replicate. And because we're using oxygen, if we were to just give 100% oxygen, getting to some sort of plateau would take a very long while. So what we've done here is that we give people 21% oxygen for a couple of minutes. We give them 30 seconds of 100% oxygen, allowing a very high gradient, and therefore being able to push the oxygen level up quite quickly. And then we swap to 50% oxygen, 50% medical air to get a 60.5% average, which then we hit this plateau much more rapidly. We repeat that 2 times. And we use this sequence, these sequences from the Munich group we've been collaborating with. So a 3D Gray sequence to measure multi-echo, spin echo, R2 measurements. And this should say 2D. It's a 2-dimensional multi-echo, gradient echo sequence. And then a relatively high resolution BOLD EPI sequence, gradient echo for our hyperoxia BOLD, and a local implementation of Trust. Oh, and of course, we also use this non-reviewing mass circuit inspired by Felipe Tancredi's model, but using the modifications that Sana Suri is using in Oxford. In terms of analysis, it's all the Trust OEF is using a local sort of script, but based on calibration from Pando Liu, and in order to estimate the oxygen extraction fraction, assuming 100% saturation of the arterial blood. On the HM qBOLD, the hyperoxia multiparametric qBOLD side, we've got these parallel tracks of hyperoxia BOLD analysed by using F-cell feet to be able to get the percentage change in BOLD signal, and then using this heuristic model to convert that into a percentage blood volume. And then on the mqBOLD side, we can fit R2 for the multiple spin echo and R2 star for the multiple gradient echo, and use subtract it R2 prime, combining together to get the OEF. And with the aim of comparing this whole brain measure with this, the average grey matter OEF. And here are some of the results. So from the multiparametric, from the hyperoxia multiparametric qBOLD, we see the R2 prime values very similar to previously measured, so in a sort of range of 6 to 7 hertz. DBV is very similar to what we measured previously, the order of 1 to 2, well, maybe 2 to 3%. But our AF values are quite unphysiological in that one of the values is almost 200%, on average around 117%. We'll discuss that a little bit more in a moment. In terms of then comparing that to the values from Trust, ever reliable as it is, gives us a nice average of about 38%, which we'd expect, and obviously some variance across the group, which also we would expect. So far, we haven't really run any correlations on this to see whether it's whether at least it may be a relative measure of OEF. But we've got another 12 participants to add into the analysis, so we'll see how that works in the longer term. So from a discussion point of view, clearly our R2 prime values from multiparametric qBOLD are very similar to what we thought previously, but they're also clearly a lot greater than we'd expect from a more direct measurement. So this data that Alan's got is he also got some Jesse data, so we'll be able to see whether we can do some qBOLD measurements with that Jesse data, but also measuring R2 prime and comparing those values between the multiparametric and the Jesse for looking at correlation between those and whether there's some clear scaling between the measures, which might bring our OF values down. The DBV values are consistent with past measurements and realistically more relevant for qBOLD than using gadolinium. And if you don't use gadolinium, that's always a benefit. But yeah, clearly not in agreement with the OF trust at the moment, vastly outside of physiological range. But as I say, hypothesized to produce overestimation of R2 prime by qBOLD. As I say, future work aims to to analyze further subjects to assess the correlation between these two measures, and hence where we can use it as a relative measure of OEF. But we're also doing some, Atom's working on a phantom experiment to try and look at how you might translate this technique to other vendors. And so far, the results of that show that gradient echo sequences are very similar across vendors, but the R2 measurements can be drastically different. And so experiments like these, where we compare more direct measurements of R2 prime with a multiparametric approach, might be required to be able to look at how those things can be corrected or accounted in the future. So yeah, that's all. And for any questions.